Well, hello to everybody and a warm welcome to you all, and thank you for joining this webinar about evaporative cooling and humidification in data centers and telecommunications applications. My name's Dave Marshall-George and I'm the UK and Ireland Sales Director for Condair. Presenting today is William Trong. William will be the main presenter, and he's going to introduce himself shortly. And we could have over 1,000 people on the webinar today, so everybody will be on mute. If you do have any questions, please submit them using the text question function in the control panel, and I'll answer some questions as we go. But when the presentation is finished in around 50 minutes, I'll be taking some of the most popular questions and posing them to our expert, William. Now, I know a lot of you have also asked for a copy of the presentation, so you can download a copy directly from the Handouts tab in the control panel. So with that, I'd like to hand over to our expert, William, who's going to deliver the presentation today. Hi, William.
Hey, Dave. Perfect. Thanks for that introduction. So thanks, everyone. So as Dave mentioned, my name's William Trong. I am a business development manager here at Condair, representing our Evaporative Technologies team. So again, just thank you everyone for taking time out of your busy schedules to join us for the webinar today. So we'll go ahead and get started here. So I'll just turn off my camera so we can focus on the slides. Perfect. So just a quick introduction to Condair for those of you who are not familiar with who we are. We are a leading manufacturer and solutions provider for humidification and evaporative cooling systems. This includes all of your traditional isothermal steam humidification systems, as well as a wide range of our evaporative and adiabatic systems, a few of which we'll talk about in depth today. We're a global organization with multiple distribution partners, sales offices, and production sites located throughout the world. So with that, we'll just jump right into the presentation here. So learning objectives today, we'll cover three main sections. So we'll start with delivering the ASHRAE window or delivering the ASHRAE window with evaporative technologies. We'll then look at the AHU evaporative strategies and how these systems can really be applied. And then finally, we'll look at the different adiabatic technologies that are available on the market today. So I'd like to start off with an introduction to the ASHRAE environmental envelope or ranges for air-cooled equipment. So for those of you that are not familiar with ASHRAE, I think the majority of the participants joining us for this session are based out of North America. But for those of you that aren't, ASHRAE is the American Society of Heating, Refrigeration, Air Conditioning Engineers. Now, although American is in the name, they are a global association with over 50,000 members and represented for more than 130 countries. So very well represented association. But in this section, we'll cover the ASHRAE operating ranges, the physics of evaporative cooling, as well as the conditions where evaporative cooling could potentially be used. So we'll start with the environmental ranges, and we'll refer here to the recommended range as well as the allowable range. So we'll start off with just a couple quick definitions here. So the recommended range is likely the most important range for data center designers and operators, and it's really the range where the servers are going to be operating for the majority of hours out of the year. The recommended range was chosen based on several factors, primarily the reliability of the IT equipment, power consumption, as well as to provide a buffer for potential excursions before reaching the allowable limits of the IT equipment itself. Now, the allowable range, on the other hand, is where ITE manufacturers test their equipment to verify full operation. However, it's important to note here that this doesn't mean that there's not going to be any impact on the IT equipment. So although the equipment may function at the extremes of the allowable range, it may have an impact on the performance as well as the reliability of the IT equipment itself. So the key takeaway here on this slide is that the IT equipment should operate within the recommended range for the majority of the year, and the allowable ranges were specifically created to allow for potential excursions that are not outside the capability of the IT equipment under extreme load conditions. And then the actual range is where the facility and/or ITE operator decide to operate their equipment. And that's really going to be a balance between optimizing efficiency, reducing the total cost of ownership, as well as addressing reliability issues and potentially improving performance. So a bit of history here in the evolution of these guidelines. Prior to 2004, guidance on the allowable environmental envelope for IT equipment really varied from one manufacturer to another. So IT industry leaders started to talk about standardization, which eventually led to the formation of ASHRAE Technical Committee, or TC 9.9, which covers mission critical facilities, data centers, technology spaces, as well as electronic equipment. So in 2004, the first revision of the guidelines were released, with the goal of really setting a standard for aligning ITE manufacturers to maintain equipment reliability. And power and efficiency were not really a focus at this time. So you can see here on the site chart that the initial recommended range for the equipment is quite small at 68 to 77 degrees Fahrenheit and a relative humidity of 40 to 55%. The next update to the guidelines was in 2008, and this was one of the biggest changes, which included an expansion of the recommended range in a desire to achieve higher data center efficiency and a total lower cost of ownership. So here we see a change in the recommended temperature range to 64.4 to 80.6 degrees Fahrenheit, as well as the addition of dew point to the humidity limits. There were no changes to the allowable ranges in this update. And this is really when ITE manufacturers and data center operators started to move away from the notion that colder is better, and by increasing the recommended temperature and humidity ranges, allowed for the increased opportunity to use compressor-less cooling solutions as well as economizer systems. The next update was then in 2011, with the allowable ranges being added, and classes 1 through 4 were renamed A1 to A4 and B and C. The new guidelines were developed, allowing data centers to operate in the most energy efficient mode while still maintaining the required reliability. So the addition of the allowable ranges A3 and A4 were created to achieve the most flexibility in the operation of the data center and really opened the potential for the use of free cooling systems in many of the world climates. And then finally, the 4th and 5th editions were released in 2015 and 2021 with relatively minimal changes compared to previous years. So in 2015, the minimum allowable relative humidity was lowered to 8% after ASHRAE funded research showed minimal impact on electrostatic discharge induced damage. And then in 2021, the upper limit for the relative humidity was actually adjusted to be dependent on the level of gaseous pollutants in the airstream. It also included an additional high density environmental class that was added. So you can see that over the years, as this guideline progressed and was updated, with each subsequent update, the temperature and relative humidity ranges were expanded in an effort to really drive opportunities for efficiency improvements. So now that we've looked at the ASHRAE recommended and allowable ranges, let's look at how evaporative cooling can be used to complement an economizer system to deliver these conditions more efficiently than traditional mechanical cooling. So we'll look at the psychrometrics on the next slide, but when we talk about evaporative cooling or the adiabatic process, we're referring to the evaporation of water into an airstream. So we're taking water and converting it from its liquid state to its gaseous state, and to do this requires a certain amount of energy. The energy in this case is heat energy from the airstream, which is transferred to the water, resulting in a decrease in air temperature, as well as an increase in moisture content. Now, the main benefit of adiabatic cooling over mechanical cooling is the ability to provide a significant amount of cooling at an extremely low energy consumption. The only energy that we're using is already in the air, and we're not using any additional mechanical cooling equipment. So to put this into perspective, to evaporate 1 kilogram or 2.2 pounds of water requires about 680 watts of energy. That is the amount of energy needed to drive the phase change from liquid water to gas. So that means for every kilogram, every 2.2 pounds of water that we evaporate, we can actually achieve 680 watts of cooling with that as well. Now, the caveat to this process is that that supply air does need an initial low humidity level in order to allow for that moisture to evaporate and provide the cooling. Because air can only hold a certain amount of moisture, if the moisture content or the humidity is already high, the amount of evaporation and cooling that we're going to be able to achieve is going to be relatively limited. So let's take a look at what this process looks like on a site chart. I'm sure many of you are familiar with this chart, but we'll quickly go over just a few of the basic elements here. So on the bottom, we have the dry bulb temperature. We have the wet bulb temperature going diagonally across the chart from left to right. We've got the relative humidity curves going here from right to left. And then we have the absolute moisture content on the sides. Now, from two of these parameters, we can actually derive several others. So if you have, for example, a dry bulb temperature and either a wet bulb temperature, relative humidity, or even moisture content, you can actually derive the specific enthalpy, which are shown on the sides of the chart here. So on the diagonal going across and then along the bottom here. Now, specific enthalpy is actually a key parameter for us because the adiabatic process is actually a constant enthalpy process. So we'll follow those lines of constant enthalpy. So if we know a starting condition or starting point on this chart, we can actually plot that adiabatic process out. So with that in mind, I'll hit play here. So if we know a starting position, we can actually adiabatically cool along the line of constant enthalpy, and we can see what our leaving air condition is going to be. But what I want to point out here is as we go down that line of constant enthalpy, we actually have a temperature decrease, and then we also have an increase in moisture content. So this will be important when we start looking at how evaporative cooling can be used to achieve the desired supply air conditions to a data center. So when we look at the ASHRAE recommended and allowable ranges, we can see that by expanding out the acceptable operating range for a data center, we can actually increase the potential use for economizer and evaporative cooling. So if we have an outside air condition that's already within the acceptable range, whether you're operating in the recommended range or anywhere from A1 to A4 class, you can actually just pull outside air, bring that into the data center and use that for cooling. But if you have what we're showing here in the blue regions, if you have a supply air condition or mixed air condition that falls within this range, you can actually adiabatically or evaporatively cool that air to get you to the range that you want to operate in, whether it's the recommended range all the way through A1 to A4. So you can see that as we expand out the potential operating range for the data center, the number of operating conditions or hours out of the year that we could potentially operate in an economizer with evaporative cooling expands quite a bit when you go from the recommended range all the way through to A4. Now, the second point that I want to make here is that we know that water consumption and sustainability is a huge topic these days, and there's a push to reduce water consumption within data centers. And we know that evaporative cooling uses water. There's no getting around that. And depending on the size of the data center, that can actually be a significant amount of water usage per year. So by moving or expanding out from the recommended range into the A1 through A4 class, you can potentially reduce the number of hours that you would need to operate on an evaporative cooler simply through the expansion of the allowable temperature range that you're willing to accept within the data hall. So if you're already running a data center with economizer and evaporative cooling, but you're concerned about water usage, that's one way to potentially reduce the amount of water that you're using simply by adjusting those temperature ranges and adjusting the point at which you turn on the evaporative cooling system. So up until now, we've talked about evaporative cooling for the purpose of cooling, but the other potential use case here is the benefit of evaporative cooling for humidification. Because evaporative cooling works through the evaporation of water, if you remember, as we cool that air, we're also increasing the moisture content or the relative humidity of the air. Now, if you remember, the ASHRAE recommended and allowable humidity range is actually quite low and goes as low as about 8%. And in most places around the world, the outside air humidity will be above that, so really no additional humidification is going to be required. But in our experience, even though the low end humidity range is 8%, we do still see designers looking to achieve a minimum of about 20% relative humidity. But again, this will be entirely dependent on the facility and where they decide to operate their equipment. So what we're showing you here on this map in the regions of blue are cases where we would experience temperatures below 32 degrees Fahrenheit or 0 degrees C, and looking for a target supply air temperature of around 64 degrees Fahrenheit, 18 degrees C, and a minimum 20% relative humidity. If we were to simply take that really cold outside air and heat that without any additional humidification, we'd likely be below that 20% minimum. So we'd need some form of supplemental humidification. And we've got a really great case study that shows this, and we'll talk about this later on in the webinar. But the main point here is that if we have really cold air outside and want to bring that into the data center, as soon as we heat that up, there's a good chance that that's going to drop the relative humidity below an acceptable limit. So now that we've looked at the ASHRAE operating windows and how evaporative cooling can be used to help achieve them, I want to move into the different evaporative or adiabatic strategies and how they can be applied within an air handling unit or a duct or a plenum. So we'll look at direct versus indirect evaporative cooling, as well as direct humidification. And for each of these strategies, we'll also look at how these systems are typically configured, as well as a live case study for each, showcasing the potential or actual energy savings that have been achieved in deploying these strategies. So we'll start with the most basic, which is a direct evaporative cooling system. So in this case, we're taking fresh outside air, we're running that through a filter, and then through an evaporative or adiabatic cooling system. So if you remember, we're evaporating water to the air, resulting in a decrease in dry bulb temperature, as well as an increase in relative humidity, and that is being supplied directly into the space. On the other side, we've got return air coming back from the space, and that's simply being exhausted out. So the key here for direct evaporative cooling is that we're treating the air, we're dropping the dry bulb temperature, but we're also increasing the relative humidity, and that air is being supplied directly to the space. Now, there are ways to take advantage of the adiabatic cooling effect without adding moisture to the supply air, and we'll touch on that later when we start talking about the indirect strategy. So the benefits of this system are that it can deliver a significantly high amount of cooling. If you remember, 680 watts per kilogram or 2.2 pounds of water that we evaporate, as well as the potential for humidification in winter months. Now with this system, however, there are some limitations. It does typically require high ventilation rates in order to maintain that cooling capacity, and it's not really suitable for humid climates where that evaporation is going to be limited. So the strategy is really ideal for hot, dry climates where the air can hold more moisture. And then, of course, the other consideration here for this type of system is going to be filtration, which is important if we're trying to keep out any outside particulate or contaminants from entering the airstream or supply airstream. So our case study for this strategy is actually from a UK-based AHU manufacturer called Weatherite. The objective here was to replace existing 30-watt compressor-driven cooling systems with a refrigerant-free, energy-efficient solution for low to medium heat density telecoms rooms for one of the leading telecoms providers throughout the UK. And one of the design requirements here was that the footprint for these new systems needed to match that of the existing DX cooling system, so they could easily be retrofitted, and they also wanted to use direct evaporative cooling. So we worked directly with Weatherite to develop an evaporative system for this design, And this is a really great example because it shows that evaporative cooling can still be an energy efficient and economical solution on a small scale as well. So you don't need to be deploying evaporative cooling on a hyperscale level to really see the benefits. So as we've talked about previously with economizers, evaporative cooling isn't always going to be required. And a lot of the times throughout the year, you can actually achieve the cooling simply by bringing in fresh air. So this system actually has two operating modes. Mode 1 is going to be free cooling. And how this works is at the top of the unit, we have a recirculating air damper. Recirculating air damper at the top here that when open allows for air to be recirculated or mixed with fresh air. Or if we close this can be used to exhaust air to the outside. On the right side, we've got our fresh air supply coming from the rear of the unit. That's going through a set of filters. And then on the bottom here, we have the bypass damper. So when cooling demand can be satisfied with circulating air, fresh air, or combination of the two, they can mix in the supply air section at the bottom of the unit and be supplied to the space. So if you look at the photo on the left side, you can see the supply air grill just on the bottom of the unit. So looking at the photo here, you can actually see the evaporative system that we've got installed inside this unit. In this case, it's a glass fiber evaporative media system, which is activated when the demand can't be satisfied using outside air only, and evaporative cooling is going to be required. So in this case, we move into mode 2. And how this works is the bypass damper is closed. So all of the air is forced through the evaporative media system. The media is going to be fully saturated with water. And as the air goes through that evaporative pad or evaporative media, it's going to cool and humidify the air. This can be mixed with recirculating air, return air from the space if needed, mixed in the supply air chamber, and then supplied directly into the space. Just a few points here on the evaporative system. So this is a recirculating evaporative system. So we do have a small sump inside the unit and then a small single pump there that's used to pump water to the top of the media. Any unevaporated water falls back into that sump and we'll continually recirculate that water, periodically draining some of that water out in order to maintain a specific water quality. And that really just helps to maximize water efficiency within the evaporative system itself. So as you can see, overall, a relatively simple system in terms of the design and the operation. But what does that actually mean when we compare the new adiabatic system to the legacy 30 kilowatt DX system? So we've got a lot of data here on the screen, but we'll break it down for you. So on the left side column, we have the ambient air temperatures in degrees Fahrenheit, so going from 23 degrees all the way up to 95. Next column over is the number of hours out of the year that we'll experience those temperatures. So we can see how many hours we'll experience those temperatures and the number of hours that we would potentially need to be cooling that air down. And then the next two sets of data show the performance data for the 30 kilowatt adiabatic unit, as well as the 30 kilowatt DX cooling unit. So if we look at the ambient air, outside air condition and associated operating modes, we can see that at 59 degrees, both the 30 kilowatt adiabatic unit and the DX system are going to be operating in free cooling mode. So simply pulling outside air, bringing that into the space and supplying that for cooling. So if we look at the absorbed power for both, the 30 kilowatt unit is going to be drawing about 1.5 kilowatts compared to about 2.45 kilowatts. So as expected, relatively close because they're both running in free cooling mode. We do notice a small decrease here on the 30 kilowatt adiabatic unit, and that's really because they've got slightly more efficient fan motors and fan blades in that unit. But the change really occurs when we're above that 59 degree mark, moving into the 68 degree Fahrenheit supply temperature range. So the previous system would be running in DX cooling mode, and the new system, the adiabatic system, would be running in evaporative or adiabatic mode. And you can see here that the absorbed power when we look at the two, so comparing first the adiabatic unit, going from free air cooling to adiabatic, goes from 1.589 to 1.66 kilowatts. So relatively small jump or increase in power consumption. We do expect that increase really because the air is being redirected through the media. So a little bit more fan power required to push the air through the media itself. But you'll notice that on the legacy DX cooling unit, going from free cooling mode to DX cooling mode represents a significant jump from 2.45 kilowatts all the way up to 23 kilowatts. So huge difference there. And when we calculate the cumulative effect of the run hours between the 30 kilowatt unit compared to the adiabatic unit for the year, we can see that for the DX unit, annual consumption is going to be around 70,814 kilowatts compared to 14,088 kilowatts for the adiabatic unit. So this table shows, when you're going to experience those savings, and you can see that it's when we're experiencing the higher air temperatures, the legacy equipment would have to turn on the DX cooling system, and we see that increase in power consumption. So on the side here, we have the kilowatts per year. On the bottom, we have the ambient air temps. And you can see that for the adiabatic unit throughout the year, power consumption remains relatively low. And then again, on the DX unit, as soon as we have to turn on that DX system, power consumption increases. So this equates to about an 80% reduction in energy consumption by moving to a direct evaporative cooling system from the traditional DX system. So huge savings, especially when we're considering that there are hundreds of these units installed out in the field. So overall, a really, really successful project. So that was with direct evaporative cooling, but what if we had a case where we don't want the relative humidity to increase, but we still want to use the evaporative cooling or the free cooling effect? So in this case, the other method of applying these technologies is through an indirect evaporative cooling system with the use of a heat exchanger. So in this case, we're taking our fresh air stream, which is cooled adiabatically, to as close as saturation as possible. So the highest moisture content, lowest possible temperature. And because we don't want that moisture to be supplied to the space, we'll use a heat exchanger like we would a traditional coil. So we'll pass that evaporatively cooled air through one side of the heat exchanger, and then we'll simply exhaust that out. On the other side, we've got our return air coming from the space, going through the heat exchanger, cooling that air sensibly, and then being supplied back to the space. So the same concept as if we were to use a coil. However, in this case, we're using an evaporatively cooled air supply to cool a heat exchanger instead of a chilled water supply to cool a coil. So in applications where you don't want the air streams to mix, such as a secured building, this would be an ideal strategy. The amount of cooling that we can actually achieve can be increased by circulating more air. And of course, we're not adding moisture to the airstream. We're only sensibly cooling it by going through that heat exchanger. The other benefit with the strategy compared to the direct evaporative cooling systems or strategy is that we're not limited to the extraction rate or fresh air rate. And of course, generally, this type of system will have a higher cost compared to a direct evaporative cooling system. And the efficiency itself will depend on the efficiency of the heat exchanger or heat recovery unit that we're using. So now let's look at a case study that utilizes this indirect evaporative cooling strategy. So this is a project for the Cork Internet Exchange in Ireland. And the objective here was to provide cooling to a newly built data hall using air-to-air and evaporative cooling technologies only. They did not want to use any DX expansion cooling, so no chillers or mechanical cooling systems with this building. So we worked with the leading air handling unit manufacturer to supply the evaporative systems for this project. So we'll go through the schematic here before we start drawing in kind of the arrow showing the process. But this is a schematic of the air handling unit that was designed for the data hall. So we'll go through this stage by stage. So if we draw a straight line down through the building or through the unit, Each side is mirrored, so the left side and the right side are both mirrored, and there are 4 circuits of airflow in the system. So we have the outside air that's drawn through the evaporative cooler, where of course, if it's needed, we're going to evaporatively cool that air, resulting in decrease in temperature, increase in humidity. That's going to go into the mixing area, where it can be mixed with exhaust air, depending on the controls and if it's needed. The air then goes down through a damper, then through a set of heat exchangers. So through the first heat exchanger, through the second heat exchanger, back up into the exhaust air plenum, where it can be exhausted out or recirculated back in. On the other side of the heat exchangers, we've got air coming from the hot aisle, split left and right because it's a mirrored building, goes through the first heat exchanger where it's cooled sensibly, goes through the second heat exchanger where it's cooled down further, back into the cold aisle, picks up heat from the IT equipment where it's sent back up through the heat exchangers and continues to recirculate around. So just wanted to explain that before we start drawing in these arrows. I'll play here. Can get a little busy, but we'll go through it again with the arrows. So warm outside air coming in, evaporatively cooled in the mixing area, through the first heat exchanger, through the second heat exchanger, exhausted out. And then on the other side, from the hot aisle, going through the first heat exchanger, it's cooled sensibly, through the second, cooled down even further, supplied into the cold aisle, and then continually recirculated. So again, just like having a cooling coil, we're taking warm air, cooling it sensibly and putting it back into the space. Only in this case, we're using an evaporatively cooled heat exchanger instead of a chilled water coil. So this is what the system looked like inside. And just to give you an idea of scale, got a small step ladder just beside the unit. So again, air drawn up from the hot aisle, through the first heat exchanger, through the second heat exchanger, supplied back down to the cold aisle. And then on the other side, outside air, evaporatively cooled, supplied through the first heat exchanger, through the second heat exchanger, and then exhausted out, and then just mirrored on the other side. And here you can see some additional photos of the air handling design. So quite an impressive design here. So when we looked at the power demand for the unit, we were of course using free air cooling whenever possible. So what we're looking at here is the orange line. So you can see that at the lower ambient air temperatures, we're running in just air-to-air cooling mode. So we don't have the adiabatics on yet. As soon as those temperatures start rising, we'll turn on the evaporative cooling system, and that's when we start seeing the increase in power consumption. But what we want to point out here is the actual power demand versus the actual cooling load. So you can see that we're going from about 12 kilowatts all the way up to about 25 kilowatts of power. But at that max, when the evaporative cooling system's operated, we're drawing 25 kilowatts of power, but we're actually supplying close to 400 kilowatts of cooling. So a huge amount of cooling for a significantly low amount of energy input to the system. So a few more project details here. There were 4 of these 400 kilowatt modules installed. Return air was 104 degrees Fahrenheit coming from the hot aisle. Supply air temperature was 78.8 degrees, and the heat exchanger efficiency was 80%. And then the electrical consumption for each of the 400 kilowatt modules was between 11 and 25 kilowatts, with an annual average of about 12 kilowatts. So this gave an overall power utilization efficiency, or PUE, of less than about 1.4. So compare this to the previous legacy design, which resulted in about 75% less energy required by going to an indirect evaporative cooling system on this new design. So now we'll look at our final strategy, which is using evaporative technology or evaporative systems to increase the humidity without necessarily using it for the objective of cooling. So we saw earlier that when we looked at the world map, this type of humidification can be very beneficial when we've got a free air cooling system in cold regions where we've got potentially waste heat or excess heat available for reheat. So as soon as we take that cold air, heat that up to be able to supply that to data center, good chance that we're going to be below a minimum threshold humidity. So proactive moisture addition is going to be required. Benefits with this type of system for humidification is very low energy humidification if used with heat recovery. So if we've got a lot of waste heat available, like we would have from IT equipment, as well as high capacity humidification with very little energy input. So just to give you an idea, 200 pounds of humidification done through a traditional electric or isothermal steam system is going to require about 75 kilowatts of electricity. Our evaporative system, on the other hand, if you can evaporate the amount of water, can actually output about 2,200 pounds of humidification, which in the end would consume less than 0.3 kilowatts, because the only energy that we're putting into the system is the energy to run the pumps to pump water to the top of the media. Limitations here, of course, are going to be that if the cooling isn't needed, you may need to preheat the air in order to offset that cooling effect that we get from the evaporation of the water. The other limitation is generally on the hygiene side, where we're going to see potentially more stringent hygiene requirements with an evaporative or cold water system when compared to an isothermal system where we're boiling the water, generating steam for humidification that's going to kill off any potential bacteria that's in the water. So just something to consider there when we move to adiabatic or evaporative systems for humidification, just the hygiene side of the water quality. So the case study that we have for you here is actually a meta data center located in Luleå, Sweden. And the objective was to maintain a minimum humidity level across a large data center that's located just outside the Arctic Circle while operating solely on a free air cooling strategy. And the humidity range here for this design was in the range of 20 to 80%. And given the climate for this part of Sweden, temperatures can actually drop as low as minus 40 degrees Fahrenheit. So once that air is introduced into the building, heated back up, indoor humidity without any proactive or supplemental humidification would likely drop that as low as about 2%. So humidity control in this case was actually a necessity, and with the massive air volumes that we had, evaporative humidification with the preheat available, using hot air from the data halls was a really economic and efficient solution. So here we worked with Kundal, the consulting engineer, as well as Bravita, the contractor to supply the evaporative systems for this project. So here we can see a schematic of the system, which in this project, it's referred to as a penthouse ventilation system. Each one is referred to as a lineup, and there's 13 lineups per data hall with 2 data halls in this building in particular. So one lineup consists of an intake plenum, return plenum, filters, humidifier, supply fans, relief fans, and then dedicated controls for each of those. So as you can see on the right side, we've got cold outside air dampers, cold air coming through the dampers, bringing in fresh air. We have hot air coming back from the space where it's mixed in the mixing plenum with the cooler outside air. That mixed air then goes through a set of filters, then through the evaporative media system here. This was a evaporative media system consisting of glass fiber media with a water recirculation or pumping system. And then that humidified air and cooled air supplied down to the data hall. And then on the left side, we have our exhaust air plenums. So a couple actual photos of the install here. In both photos, you can see the evaporative media system on the left side. In the first photo, we've got the filters on the right side. And then on the second photo, we've got the supply fans just on the other side of the humidifiers. And then you can see here, this is actually a double stacked evaporative module. And we've got multiple units spanning the entire length or width of that building. Another image here, a couple images. The first one is actually showing the evaporative systems with the lights off. You can see a slight glow that's coming from the bottom of the sumps, and that's actually a submerged UV sterilization system that we use for hygiene. So we talked about hygiene for these types of systems, and UV treatment is actually a really common hygiene control method used in evaporative systems. And then the other image here on the right just shows the air supply down into the data halls. So the supply air temp range for this design was 64.4 to 84.2 degrees Fahrenheit with humidity range of 20 to 80%. Outside air temperatures ranged from minus 40 to 86 degrees, with temperatures very, very rarely actually rising above that 86 degree mark. However, in that case, we could also use these evaporative systems for the cooling as well. Fresh air rates range from 18% at minus 40 degrees, all the way up to 100% when the ambient air temperatures were less than about 64.4 degrees. So in the end, we ended up supplying 52 evaporative systems with a max humidification load of about 25,794 pounds an hour, but a total humidifier max power usage of only 32 kilowatts. So there's no mechanical cooling, no additional systems installed here for cooling. So overall PUE ended up being around 1.07. So if you were to compare the power consumption used for the evaporative systems for humidification compared to, say, a more traditional electric or isothermal steam system, the evaporative systems would actually represent 99.7% less energy consumption. So huge potential savings from the humidification side. So we've looked at the ASHRAE environmental envelope and how evaporative cooling can help to achieve supply air conditions within those ranges, along with the strategies and how they can be implemented. So now I just want to take a closer look at the actual adiabatic technologies that are available in the market today. So these will include the evaporative media system that we just talked about, high pressure atomizing systems, a relatively unique hybrid system that's available from Condair, and we'll also touch on chiller pre-cooling with adiabatic technologies as well. Now, just for the sake of time, I won't be going in depth on each of these technologies, but we do have a number of other webinars available online that are available to watch anytime on demand that cover these topics. And then certainly if you have any questions related to any of these topics or any of these specific products, don't hesitate to reach out. So the first technology that we'll look at here is an evaporative media system. So this is known as a wetted media or wetted pad system, evaporative cooler, wet wall. You may have even heard this referred to as a swamp cooler before as well. But this is probably the most common type of adiabatic or evaporative system that we see in the data center market today. And how this works is it's typically sized to match the internal dimensions of an air handling unit, duct, or a plenum. And we can actually have multiple units installed as well, like we saw with the Meta case study. But relatively simple in terms of principle of operation. We're taking air, we're passing that through an evaporative medium. In this case, we're showing a glass fiber media or glass fiber matrix. There are other materials that are available in these types of systems as well, but glass fiber is generally the most common in data center applications simply due to the flame and smoke ratings that are required. Now, there will generally be a water supply and a sump or pump system to the unit as well. So when we have a demand for cooling or humidification, water supply will fill the sump. We'll start pumping water over the media. Water then cascades down over the media, eventually fully saturating it. And then as air passes through the media, a portion of that water is evaporated into the air, which of course gives us that decrease in dry bulb temperature and increase in relative humidity. Now, one of the main benefits to this technology is that you don't need water treatment with this type of system. Because all of the evaporation takes place within the depth of the media itself, any minerals that are in that water that will potentially precipitate out as a result of the evaporation will either get flushed out or will form a scale on the media, and eventually that media would need to be replaced. But to help with scale in these types of systems, we do typically have a bleed cycle that's controlled through a water conductivity sensor or a timer. And I just want to make a point here that water quality, cycles of concentration, scale formation, and how that impacts media life is probably a whole other topic that we could spend a couple hours on. But if you are interested in learning more about this, we do have some really great blog articles available on our website that take you through this in depth. So if you're interested in learning more, be sure to check those out. Now on the design side, a couple considerations here. One of the main ones being media velocity, and then of course control accuracy. So media velocity or velocity onto the media will actually have an impact on the efficiency of the system, as well as the potential for carryover. So when we're talking about efficiency here, it's how much water can we evaporate into the air and how far up that line of constant enthalpy can we go. So the efficiency of the system is going to really determine what our leaving air conditions are going to be. And what that comes down to is really the contact time between the air and the water. So if we have a higher velocity, we have a lower contact time between the air and the water, and we have a lower evaporation efficiency. The other issue if the velocity is too high is that there's a risk for that high velocity air to pull water droplets off of the media into the section downstream. So typically these systems are designed around media velocity of about 3.5 meters per second or about 700 feet per minute. The other consideration is, of course, the controllability. Because the media will take some time to fully wet and dry, there's going to be a ramp up time and ramp down time that needs to be considered. So in order to help with that, systems will typically have some sort of staging where only certain sections of media will be wetted depending on the required output from the system. But in general, control accuracies for an evaporative media system are going to be in the range of plus or minus 5 to 10%. The next technology that we'll look at is a high pressure atomizing spray system. So this system works a bit differently in that we're actively spraying water into the airstream and those water droplets are being evaporated. And that's how we're getting the cooling effect as well as the increase in moisture content. Now, one of the key differences here is because we are spraying the water, we do need to use treated water such as reverse osmosis, which will remove 95 to 98% of the minerals that are in the water. Issue is if we don't do that, minerals would potentially clog the nozzles and would also precipitate out as those water droplets evaporate, which would create a dust which could make its way downstream potentially into the space. But how this works is we have a pumping station. We pressurize the water to about 1,000 psi or 70 bar. It's passed through a set of control valves into a nozzle manifold and sprayed into the duct of the air handler. Again, here, efficiency of the system is going to come down to contact time between the water droplets and the air. So the higher the velocity, the lower the evaporation efficiency. The other part here inside of the duct is we do also have a droplet separator or mist eliminator. And that's just going to capture any of the unevaporated water and prevent it from carrying over downstream. Now, the distance between the nozzle grid and the droplet separator, we typically like to see about 5 feet or about 1.5 meters, really to give us enough time for that water to evaporate before it hits any obstructions. We can go shorter in that section, but of course, that's going to lower the efficiency of the system as well. Control accuracy with this system is generally a bit better than an evaporative system. The way that we control or modulate the system is we have a set of control valves, and each of those control valves is connected to a different number of nozzles. And then simply by activating or deactivating nozzles or valves in specific combination, we can actually achieve pretty good modulation or staging with this type of system, which gives us a control accuracy in the range of plus or minus 5%. The next technology that we'll look at here is a combination of the last two, which is a unique system to Condair. So it's actually a combination of both of the systems that we just looked at. So this is a atomizing spray system with an evaporative media downstream. So it's going to work very similar to the high pressure system. We've got a water treatment system, so typically carbon filter, softener, RO, going into a pumping module. We're pressurizing the water, slightly lower pressure here, about 100 psi or about 7 bar. Going through a set of valves into a nozzle grid, we're going to spray that water directly into the air handler of the duct where it's evaporated. And the big difference here is downstream from there, instead of a droplet separator, we actually have an evaporative media. And in this case, it's actually a ceramic, very porous ceramic tile that allows for post-evaporation as well as acts as a droplet separator. And what that allows us to do is actually shrink that absorption distance or that install length from about 5 feet down to 2 to 3 feet. So we can actually save a significant amount of airway length by going to a DL type system. Staging works very similar to the high pressure system where we've got valves connected to different number of nozzles, but we also have the ability to vary the pressure to the nozzles as well, which gives us a bit more controllability. So we're able to achieve about a plus or minus 2% control accuracy with this type of system. So when we compare the three technologies, there's 5 main comparison points. We typically compare water consumption, energy consumption, pressure drop, control tolerance, and then finally the air handling installation requirements. So when we look at the evaporative media system, water consumption is relatively low because we can use mains water, typically 1.1 to 1.2 times the evaporation rate, including flush cycles, and you can use mains water. Energy consumption is relatively low, generally less than 0.5 kilowatts per system. On the pressure drop side, going to be slightly higher than the others simply because we have to push the air through a thicker evaporative media. And then of course the wet up, dry out times result in a control accuracy of about plus or minus 10%. But other difference here is the air handling material here can be standard. We don't need full stainless steel wet sections. When we look at the high pressure system, water consumption is going to be high. Main reason for that is because we do need reverse osmosis water. With a typical RO system, we're going to expect a minimum of about 50% of that water going into the RO system to be rejected out. So that does always need to be considered in the overall water consumption of the system. Energy consumption relatively low at less than a kilowatt. Pressure drop will be lower compared to the evaporative media system since we've got a significantly thinner droplet separator. But the air handling material does need to be a full stainless steel wet section. And then finally, with the hybrid system, water consumption is going to be somewhere in between. We do still need the RO reverse osmosis water, but because we have the higher evaporation efficiency from the ceramic media, we're going to have less water that's unevaporated inside the airstream that's going directly to drain. So slightly better pressure, slightly better control accuracy. Pressure drops can be slightly higher because we do have to push the air through the ceramic media. And then of course, because we are atomizing the water, it does need to be a full stainless steel wet section inside the air handler. So as a final technology, or really an application that I want to touch on just very briefly here, is pre-cooling using adiabatic or an evaporative system. So there's been a lot of talk, or there is a lot of talk in the industry about transitioning from air cooling and evaporative cooling towards liquid cooling. And I think the landscape for liquid cooling is still really yet to be defined, especially at a large scale, but it is evolving relatively quickly. So what I want to point out here is that even in a liquid cooling system, whether it's a liquid to air cooling system or a liquid to liquid cooling system, there's still going to be some form of heat rejection equipment, and that heat rejection equipment can still benefit from evaporative cooling. So for example, if we talk about air-cooled chillers, what we're seeing now is a demand for evaporative pre-cooling for these systems to help pre-cool the air before it's applied to the chiller. So as ambient air temperatures begin to rise and existing chillers may struggle to keep up, if you're designing around a peak design day, which may only happen 10, 20, 30 hours out of the year, you may actually be looking at upsizing your chiller. Where an evaporative cooling system can help is by cooling the air adiabatically on those extreme days. Your chillers can still operate within their design range and can actually help reduce the overall load on the cooling system, potentially keep you from upsizing your chillers. And the most common technologies that we see here are going to be the evaporative media system and some form of atomizing nozzle system. Now, some manufacturers do offer this as a standard with their packaged chillers or equipment, and there are also products that can be used to retrofit existing installations as well. So I just want to wrap up here and just talk about some additional services that we offer here at Condair. So in addition to all of the technologies that we talked about here today, we do have an extensive service offering as well. So we offer installation and preventive maintenance across all of our products. And we do also offer on the media side what we call the KEEP program, which is a more data or metric driven approach to help you decide when and if your evaporative media needs to be replaced. And we offer full wet section maintenance as well as media changeout services as well. And then of course on the engineering side, we can help with psychrometric analysis to help determine if or what the performance of an evaporative cooler would be in your design. And if you're unsure whether evaporative cooling would even make sense in your application, we can certainly help evaluate that as well. And then finally, we do offer media scaling analysis, which can help with site selection. So particularly with the water quality that's available on site and how that would potentially impact the media life if you're using an evaporative media system. And then of course on the system specific designs, if you have a specific requirement or specification for your evaporative or adiabatic system, we can help with the engineering on that as well. So that wraps up our presentation. I know that was a lot of information to cover in an hour. So again, I really appreciate everyone's time. And I think Dave will open it up to some questions.
Yeah, thanks very much, Will. That was a fantastic presentation. We've had some really interesting questions, and I've tried to collate them and summarize a little bit. But one of the ones I'd like to start off with is, how do you prevent the air becoming too humid for the data center when using evaporative cooling?
Yeah, so typically, that's a really great question. So one of the benefits, if you're using an evaporative media system, compared to say a traditional isothermal system, it's really hard to actually go through that saturation line if you're maintaining temperature. But what we would typically have installed is a high limit control. So we'll measure the humidity level downstream from the system, typically set at 80, 85%. As soon as we hit that, we'll start turning off the unit. If you are using an evaporative system where we talked about that ramp up and ramp down time, you may want to set that a bit lower because we may still have some post evaporation off of the media once you stop putting water over the system, but generally done with a high limit switch.
Perfect, thanks, Will. What about hygiene management? How's hygiene management undertaken within these kinds of systems?
Yep, other really great question. So like I said, anytime we move from an isothermal system to a cold water adiabatic system, hygiene is always a huge concern for us, especially with Legionella. In all of our systems and a lot of the systems, you're going to have some sort of water management feature. So the key for us really is water movement. The problem with hygiene or these types of systems is if you have standing water for more than about 24 hours. So in the evaporative systems, we'll periodically drain water out of the system. On our high pressure or atomizing systems, we'll periodically flush or pulse the water just to keep it moving. And then of course, we've got UV treatment on our systems as well. And then comes down to kind of your water management plan for the rest of that.
Excellent, thanks, Will. We've got another kind of related question as well on water quality or particularly softened water. Whether people are asking whether we should soften the water. What's your opinion on that?
Yeah, I would say softened water for evaporative systems is certainly an option, which can actually help reduce the amount of hard scale formation. So when we soften the water, we're replacing the minerals, the really hard minerals, with a softer sodium. So it becomes a lot easier to redissolve that sodium in the water as we pass water over the media. But for softening, wouldn't really recommend that for any type of atomizing system. Generally, we do require reverse osmosis, simply because with an atomizing system, we're spraying that water out. The way that a softening system works, we're replacing hard minerals for soft, so we're still going to have that issue with potential precipitation. But for an evaporative system, softening is definitely an option to reduce hard scale buildup or mineral buildup on the media.
Brilliant, thanks, Will. We do have another question about how an evaporative cooling system is affected by a partial load demand. So how would we control the output of the unit? How would we modulate the unit?
Yep, great question. So I talked about that very quickly on the presentation when we talked about staging. So generally with an evaporative media system, a lot of times you can operate that as on-off. Other times you can operate that with staging. And the way that staging is done is by wetting certain portions of the media depending on the output that we need. So if we've got, 100 square feet of media in the airstream, if we need 50%, we'll potentially wet 50% of that media, leaving the other 50% dry. The other way that you can control an evaporative system is you can control it as an on-off system, but you can actually use bypass dampers or phase and bypass dampers to control a mixed air condition downstream. So you can turn on the unit 0 to 100% or 0 to 0 or 100%, and then just vary the amount of air going through the humidifier, the amount that we're actually going to cool and humidify, and then mix that with untreated air around the sides through the bypass dampers to control to a mixed air condition.
Oh, that makes a lot of sense. Will, thank you so much. We've had some, if we didn't manage to get through all of your questions, we will get back to you by email. We really appreciate your attendance and those really interesting questions. So thanks certainly for me, and thanks to Will.
Yeah, thanks everyone for your time. Really do appreciate it.
Right, we wish everybody a really pleasant day, and thanks again for attending the webinar. We wish you all well.
Thanks everyone.